Hi everyone, my name is Juncheng. Today I'm going to talk about Geocache, a group-level learned cache for efficient and high-performance caching. This is joint work with Ziming from Yale from Pelikan Foundation, and my advisor Rashmi. So let me start today's talk with a guess game. Let's guess where the people in the following two photos are going. This is the first one, this is the second one. I'm going to give people a few seconds to look at the photos. Time's up. So here's my guess. I don't know where the first person is going, but for the second one, it seems to me they're going to school. Why? Because it seems to be a group of young people carrying bags, working together in the morning. So it's likely they're going to school. So guessing the first one is hard, while guessing the second one is easier. Why? Because the second photo has a group, and it has more context information for us to make the prediction. So in other words, grouping and the context make the prediction easier. So notice the two keywords here, grouping and context. Now let's talk about caching. So caching has been ubiquitously deployed across system stacks. So there are different types of caching like block page cache, key value cache, object cache. There are different deployments within data center in personal device. When we talk about cache, usually we care about two metrics. The first one is efficiency, measured by hit ratio or miss ratio. The second one is throughput performance, measured by the number of requests this cache can serve per second. Historically, cache is fast, so we focus more on the efficiency. With the advancement of machine learning, these days, increasing more work try to use machine learning to improve the efficiency of caching. And we call these caches learned caches. We categorize existing learned cache into three categories. The first one is called learning from simple expert. Our example system is Nika. So what does it do? Let's say we have a cache, which is this box here, and we have a box of objects, which is these circles here. At some time point, the cache is full, and we need to make an eviction, which object we should evict. Learning from simple expert use two or more experts, where each expert is an eviction algorithm. At each eviction, the cache asks the two experts which object I should evict. The expert can give same or different answers, and the cache picks the expert which have made fewer mistakes in the past. So it's a nice algorithm, it's a very interesting algorithm. However, it has two problems. First, it requires maintaining two sets of metadata, which is expensive and complex. Second, it has a problem called delayed reward. This is a common problem for learned cache. What does it mean? The cache needs to know whether an eviction decision is correct or not. And it won't know that until the evicted object is requested again. And the evicted object may be requested very far in the future, and the workload may change in between. So, so this is called delayed reward. The second type of learned cache is learning from distribution. An example system is LHD, which is least hit density. So LHD models request probability over age for objects in the cache. And it may have a curve like this or like this. So it uses the request probability together with features such as size to calculate a score for each object, then evict the object which has the lowest score. However, it has two problems. First, it can only use limited number of features. Using more features requires exponentially more state space, and using limited number of features puts an upper bound on the potential efficiency it can achieve. Second, it requires sampling many objects to compare at each eviction, and random memory access in modern computer servers are very slow, so it limits the throughput of learning from distribution such as LHD. The third type of learned cache is called object-level learning. An example system is LLB, which is learning relaxed ability. LLB tracks features for each object in the cache. Then it trains the machine learning model to predict the usefulness of each object, then pick the least useful object to evict. Compared to other learned cache, object-level learning can leverage more features. For example, LLB uses over 40 features. However, it requires sampling and inference at each eviction, which significantly reduces its throughput. In our experience, LLB can be more than 100 times slower than, say, LU cache. So that's 3 existing learned cache. And today I'm going to introduce Geocache, a group-level learned cache. Geocache uses group-level learning. It groups objects into groups, and it tracks features on the group level. Then it trains a machine learning model to predict on the group level and evict the least useful group. Compared to object-level learning, group-level learning can also utilize multiple features, so it allows it to achieve potential high efficiency, while the overheads, including both computation and storage, are amortized by many objects in the group. Moreover, as we all know, most cache workloads follow Ziphian distribution, meaning that most objects only receive very few requests, such as 1 or 2. So object-level learning have very limited information to learn from. Compared to, however, groups which have many more objects, say tens or hundreds of objects, and you receive more requests, so it has more information to learn and to predict. So it makes it easier to learn. So that's group-level learning. Let's talk about the architecture of Geocache. So Geocache has object groups inside cache, and for each object group, we track a few features. And periodically, we sample some object groups, and we take a snapshot of the features. And over time, we calculate the utility of each snapshot features and use it to train a model. After we have a model, we use the model to rank groups in the cache for eviction. So it seems easy. The group-level learning is not too much different from object-level learning. However, there are a few challenges and a few design decisions we have to make. First, how does Geocache group objects? Second, what does Geocache learn? Third, how does Geocache learn? And last, how does Geocache perform eviction? Let's start from the first one. How does Geocache group objects? We use an insertion time-based grouping, meaning that as objects get written into the cache, they are grouped based on when they are written. Why do we use insertion time-based grouping? First, we observe that objects inserted at similar times are more similar compared to random objects, both in terms of frequency and use distance. Second, insertion time-based grouping is simple and generally applicable. So you do not need any special workloads or actual hint from application. So you can use it on any type of cache. Third, insertion time-based grouping can be implemented on segment or log structure storage. So we can harness the benefits of log structure storage, such as less fragmentation, higher throughput, and flash friendliness. Of course, we use, even though we use insertion time-based grouping, we can also support other groupings. Okay, so that's how we group objects. Now with object groups, how do we compare them? Unlike objects, which you can use when they will be requested in the future to compare objects, with groups, there's no such metrics. So we designed this new metric or this new utility function to quantify the usefulness of object groups. And we want the new utility function to satisfy the following properties. First, if the group contains mostly small objects, then it should have a larger utility. Second, if the group contains objects that sooner to be requested, then you should also have large utility. Third, when the group size is 1, then group-level learning effectively becomes object-level learning. Then Geocache should mimic the behavior of Bilali's mean algorithm. And last, because the utility is calculated online for the training, so we want the utility to be easy and accurate to train online. So we shouldn't need to wait for our long time to calculate an accurate utility. And here is the utility we proposed. The first one is object utility at time t, which is 1 over capital T times S, where capital T is the time to your next request to this object, while S is the object size. It's easy to see this utility satisfy the first two properties. Small objects and objects sooner to be requested have large utility. And the group utility is the sum of all the object, utility for all the objects in the group. And we can see that when group size is 1, it effectively becomes 1 over T, the utility. And it means that the object which is going to be requested furthest in the future will be the least useful. So it becomes a Bilali's mean algorithm. Similarly, the last property is also satisfied by this utility function. Okay, so with that, let's talk about feature and models. Geocache uses 7 features. 2 of them are dynamic, such as including number of requests, the number of active objects. 5 of them are static objects, including write rate, miss ratio, request rate, and insertion time, and mean object size and age of the group. We call the first 3 features contextual features, and we think they are important because many cache workload access pattern change are associated with this variable change. For example, if a daily backup happens, you may see write rate increase, miss ratio increase, and request rate increase. So that's the features. In terms of model, we use gradient boosting tree with regression as the objective. Now we have a model. Let's see how Geocache used the model. Geocache used the model to rank the groups in the cache, and it predicts the utility for each group. Then it picks the group with the least utility score, and then it chooses this group and the following few groups inserted right after it. And it uses a merge-based eviction, meaning that it retains a few objects, then evicts most objects from these groups. Notice that each ranking result or each inference is used to evict a fraction of groups. And we pick the groups with the lowest utility and the groups inserted after it, instead of picking the, say, 3 lowest utility group. This is because the objects from this group are merged into a new group. And we want the objects in the new group as similar as possible. So if we pick 3 random groups, the objects from this group may not be similar. Okay, now let's talk about evaluation. So we evaluate Geocache using 3 sets of traces, including cloud physics trace, MSR trace, and Wikipedia trace. And we use a micro implementation based on NIP cache theme, and we compare with LRU, caches, LHD, and LRB. We also have a prototype implementation based on setcache, and we compare with cachelib, LHD, and TinyLFU. Because Geocache has 3 parameters, say, for example, the group size, how many groups to evict after each inference, and how many groups to merge together. So we can run Geocache under 2 modes. One is efficiency mode, one is throughput mode. So that's Geocache E and Geocache T. Because we have hundreds of traces, so the hit ratio of these different workloads have wide range. So we show hit ratio increase over 5-fold and throughput relative to 5-fold as our metric. In today's talk, I'm going to focus on cloud physics trace with micro implementation. So this 2 figure shows efficiency. The Y shows hit ratio increase over 5-fold. The X shows different algorithms. 2 figures shows small size and large cache size. Compared to LRU, the 3 known caches, LHD, and LRB has significantly higher hit ratio. Compared to the 3 known cache, Geocache E is slightly better than all known cache, while Geocache T is similar to LRB, which is object-level learning. And this holds for both small and large cache sizes. Now let's look at throughput. LRU has no problem, which has the highest throughput, while caches, LHD, and LRB has much slower throughput. Compared to the 3 known cache, Geocache E has higher throughput, slightly higher throughput, while Geocache T has significantly higher throughput. So in other words, Geocache can achieve both efficiency and throughput. So as a summary of today's talk, I talked about the 3 types of learning cache: learning from simple expert, learning from distribution, and object-level learning. Then I introduce group level learning. If we plot this learning cache on this diagram, which has y as potential efficiency and x as throughput, the upper right corner is the best one. We will see learning from simple expert has higher throughput but limited efficiency. Learning from distribution have higher potential efficiency but also slightly lower throughput. Object level learning has the highest potential efficiency, but it has the lowest throughput. Group level learning has a spectrum of algorithm by choosing different, like say, group size, and it can achieve both high throughput and high efficiency. With that, I'm happy to take questions. And also, Geocache is open sourced at the following URL.
All right, thank our speaker.